Okay, perfect.
All
Great.
right.
Thank you
Okay,
so,
so
so
today
much.
we're hosting Maja Jablonska, who's a third year PhD student at the Australian National University, and she's got a background which is like quite much needed for our field. She's combining astronomy with computer sciences and especially machine learning techniques. And today she's going to be talking to us about her very exciting project, SPICE. And we are really delighted to have you. We can wait to hear from you. So the floor is yours. Please go ahead. Take
Thank
it
you
away.
so, so much. Thank you. And thank you for inviting me. It's such an honor and I'm very excited. So yes, I will be speaking about my main project on my PhD, which is a software designed for inhomogeneous stellar surfaces and generating spectral time series. So I think it matches very well with WST's mission. And I think I don't really have to convince the crowd here that we will have big data sets, but I just kept the slides for just to have some backing in numbers. But our current data sets are already fairly large. It will only get bigger. So even to process SDSS or the Gaia RV spectra, we need some large scale solutions. Um, and I think that machine learning is a great way to do that. It has its own challenges, but a big promise. And it's also an interesting problem machine learning wise, because we would like to see if the models grasp the underlying physics. And spectra, even from various instruments, should still be governed by the same laws of physics. So it's very interesting to see if that feature helps us to build very good machine learning models. Astronomy is generally great for machine learning. We have a lot of good data. We can simulate a lot. Even if our simulations are imperfect, scaling things up with machine learning is a very cool it's a very cool endeavor itself. So yeah, we have big data. All of them seem to be governed by physics that we understand to some extent. So that is just a great playground for machine learning. And another problem that I would like to tackle in the future is that we are somewhat limited to 1D approximation of stellar atmospheres. We don't really, at least to my knowledge, we don't really have a large scale solution to model convections or convective cells in other way than just introducing some parameters. So I included this slide from the Stagger grid, which does do a great job at modeling 3D structures of stars. But the problem is the scale. So the Stagger grid, it's also not a new grid, but when it was released, the computational constraints only allowed for a few hundred of models, and that is not really enough to have a very big overview of what's happening. So we are limited to quite severe approximations of stars, and I am very interesting to see how can we make this situation better with machine learning and some modern computational ideas and even tricks. And speaking of tricks, there is quite a cool paper from Polymatic. They do a tremendous job in implementing very cool ideas. They take very modern machine learning models such as transformers, and here they created a model named Walrus, which is designed for generally fluid mechanics. But an interesting aspect of this work is that I feel like earlier the promise was physics-informed neural networks, uh, and pins are very, very interesting, but they don't really train very easily. So people have various problems with convergence. Um, the nice thing about pins is that they do actually include some differential equations in the, let's say, in the architecture of the network. So this is why a lot of physicists were very, very excited about them. But a lot of people are then disappointed by the performance. It's very hard to train them because it's kind of an offset between goodness of fit to the data and the constraints that we ask the model to fulfill. But this study is different because it's actually not physics informed in the sense of we inject some equations. We just present data mostly from simulations. And this is based on a transformer. Transformer is a backbone of current large language models. It's a very well-performing architecture. But Polymatic team included some interesting small architectural tweaks, small, not that small, uh, or even you could say there are some very cool tricks to augment the data, and the result is really good. So they are testing this on various problems, including a convective envelope of a star. And they do admit that to really use it for a certain use case, such as modeling convective stars, you have to fine-tune it more, but the base seems quite good. So they do capture many aspects of fluid dynamics. So this is something I would be very interested to see in the future, if we could leverage models like this to have truly 3D models of stars. But that is a bit of a more future plan. Definitely not for me myself for my PhD because I have just 1 year left. So coming back to the present times, we can still model things with machine learning. We can still train models because we have a lot of data, and that is amazing. People in biology don't have such a good situation, for example, because medical biological data is hard to come by. And we are so lucky because in astronomy we have quite a good amount of observations. And if we need more, we can also simulate things. That is, of course, imperfect. We don't understand everything, but we do understand something. So at least we can include some knowledge. So machine learning models can be trained on both simulations and observations. And that is amazing because we don't really have a shortage of data. And if we do it well, they can really be fast. So they are also amortized, which means we train them once and then the inference should be much faster than what we get from repeatedly running physical simulations. So that is a bottleneck, and we can't do it for all problems. We can't just fit each point by repeatedly running physical simulations, at least not to some very high up approximation, but then we have another problems. So that is amazing because if we do it well, we train on very good data, we have a ready model that we can just apply. And um, even making things faster, I think is worth it because for large scale problems, sometimes the physics seem to be, well, we definitely don't know everything. We definitely have to be humble about this, but I think the models are really good. It's just sometimes it's just the problem of speed. So just speeding things up is great, and I feel like that is definitely doable with machine learning. And the last aspect that I have highlighted here is that I have mentioned that before, but we do expect spectra to emerge from at least for the same class of stars from similar underlying physical processes. And the laws of physics should be the same. So that is a big hope that if we train a very good base model, then we can quickly adapt it to different instruments. And that could be very useful. And then that is more of an interesting problem for machine learning researchers rather than astrophysicists. But it will be very interesting to really tackle the problem of whether machine learning models understand physics, understand or encode it in some way. We can use machine learning interpretability methods to probe if the models encode any information about atoms, if there's correlation between the lines. And actually, for example, we can see that if we train a transformer model, then lines seem to be correlated with each other. So it's kind of, it does understand, or understand might be a weird word to use because it anthropomorphizes the models a bit, but the information that lines emerge from the same species is somewhat encoded, and that is very cool. So that is the motivation for using machine learning. And now I will circle back to the astrophysical problems that I am tackling, which is the fact that stellar surfaces are not homogeneous, at least to some extent. So that depends on the types of stars, but we have spots. That's something we know from the sun. And we expect some stars to be even more spotted. Maybe some of them contain very large spots. Sometimes we can see that in photometry even. So that's a motivation that this is a worthwhile study. They also pulsate, and studying pulsations is, of course, very important for astroseismology, and that in turn influences galactic archaeology. For example, at ANU, we have a lot of people working on galactic archaeology, and I am very motivated by the idea of making astroseismological estimates better for galactic archaeology, because we do rely on the age estimates very heavily. So having an even better model and having this link between understanding spectra and ages would be amazing. One way that I would hope to achieve a better precision in that would be to model pulsations even better and leveraging spectroscopic time series for that. So the effects that I'm including in my software, which is of course still an ongoing work and will be for some time, that is absolutely fine, because this is how software lives. The goal is to provide one framework to model a few effects that are common and stack them together so that we can include all of them in our spectral synthesis and our spectral studies. And the effects that I have already included are star spots, both of temperature or abundance for chemically peculiar stars, eclipses. So planetary transits are for now treated as a special case of an eclipsing binary with a tiny secondary. In the future, of course, some atmospheric effects could be included, and that would be extremely exciting. And pulsations. And rotations is something that I have on my mind and have some plan, but would be very, very worthwhile doing for sure. And now I will present you a quick overview of how does this procedure of generating a spectrum in my framework work. It's conceptually simple. Most of the problems arise from computational constraints. So I am representing a star as a mesh of triangles. So it's just like in a video game, an approximation of a sphere, but later gets distorted because it can be flattened or it can pulsate, or it can remain spherical. So it's an approximation of a sphere containing many, many triangles, best few thousand. And each little triangle has some parameters tied to it. So it will be temperature, surface gravity, and also individual abundances. And what do we want to model is up for the user to decide, because it depends on the kind of spectrum emulator we are using. So if we want to model with a spectrum emulator that is fine-grained in the sense that we can input specific abundances, we are free to do so. But we can also just model alpha elements or general metallicity. So that is up for the user, and the framework is flexible in this regard. And then for each little triangle, we get these parameters and we put them in the synthetic spectrum emulator. And now the crucial part here is that I do not enforce the user to choose any specific emulator. And I'm using the word emulator, which is kind of also a machine learning jargon. That means that we have trained a model to learn from simulations and output something that we would expect, a good approximation of the simulation result. But in principle, this can also be just an interpolator on a grid of spectra. It's a pretty common technique to do, or even a physical code. That would be usually very, very slow, but if we really need it, that is definitely an option too. I haven't included this in my code as it is, but it is possible. And then if we are interested in a specific line, we can also include a small code that will just emulate the line, including the physical empirical quantities to the best of our knowledge. So this choice here depends on the task. It's not enforced to use any particular machine learning model. What matters is that this part gives us the spectrum, which is synthesized for this set of parameters. So we obtain a few thousand of spectra corresponding to each mesh element. And then the only thing left for us to do is to Doppler shift it by element radial velocities. It's worth noting that the angle at which we are looking at the element should already be included at this stage. So We are working on an emulator that just takes this angle as a parameter, but we can also use some darkening, limb darkening law. Again, that is a bit up to the user, but this should already be included at this stage. So then we just Doppler shift it by the element's radial velocities. Usually each element will have other velocity because there is something happening like rotation or pulsations. And then each element's projected area is taken into account to just produce a physical quantity, and then it's just summed. And then we have the result spectrum. And I have included this JAX logo here because this is very important in the computational implementation. So I really, really like JAX, and I think a lot of physicists and astrophysicists also like JAX because it can be very fast if we compile it and run it on a GPU. But maybe even most importantly, it is differentiable. So it does include autograd by default. I think that's not an overstatement, but we can leverage the fact that we obtain gradients of most functions with respect to anything we want, with some caveats, but that is computational implementational caveats. In principle, we can obtain gradients, and that is very, very cool for inference. So I have an example of a gradient of a few lines that I have taken with respect to ion abundance. And I would like to, in my next work, I would like to leverage this to test some inference techniques, starting from just a gradient descent and see how it improves our mostly, I believe, speed of inference. So we could start with gradient descent based techniques and in the future explore things like invertible neural networks to obtain parameters of a star from time series of spectra. That would be my dream. And speaking of, I have spoken about the emulator before. Now I will just show you an example that I'm using right now. My collaborator, who is a postdoc at ANU, has developed this model, transformer pane. It is a transformer-based emulator. So again, transformers seem to perform really well in various tasks. He has fine-tuned it for spectra to encode wavelengths as well. And for now, it's one for all model, but we are working on, that is not the end goal because people have different needs. And what we are working towards is to have a suite of various models. Sometimes you just need a very constrained model because you are just interested in red giants, and that is a common use case, and we would like to accommodate that. So we are working on more like a package to train various emulators for various needs. Because having a one-for-all model is convenient in the sense of you don't have to decide. But of course, it's a large model because it spans across various temperatures. It basically covers the whole Mark's grid. So it's from we have made some slight cuts because of we don't this version doesn't include molecules, so it's from 4,000 K to 8,000. It's still a big range, so the model is large. So we will work on smaller models, explore how they complement each other. So whether we have some tension on the boundaries of parameters, and that is definitely up to be updated. But you can still check it out. It's completely public. So that does work and it's all compatible. Now I will present some examples of features I have implemented and tell you a little bit about how have I approached them. Starting with pulsations. So I am very interested to see how do pulsations affect the line profiles, especially even modes, because even modes do cancel each other out in photometry. So when we have very precise photometry, it's actually really remarkable that we can squeeze out a lot of information out of photometry, but we do have information about odd pulsation modes. And basically, the more modes of pulsations we can recover, the better estimates of. I'm jumping across because this is a complicated process, but what matters for galactic archaeologists, and that is one of top fields studied at ANU, so this is why I'm so oriented towards it. one of our dreams is to have more estimates of masses and ages for standalone stars, and that can be obtained the better astroseismic characterizations we have. So the more modes we know, the better model we can build. And I would like in my next work, I would like to tackle this problem of trying to recover even modes from line profiles. So that's motivation. And now how I have approached modeling pulsations is I am just representing them as a sum of spherical harmonics, which is a convenient way for inference. Because we just have a series of parameters. I am summing them up together and I am rescaling them because the amplitude is another parameter. An important aspect here will be studying the degeneracies that arise with this formulation. So then each each combination of spherical harmonics has their own amplitude and their own period, and we can have multiple of those and stack them together. So this is an example where we stack together two profiles of pulsations. This top one is a little bit more complicated, and the second one, the bottom one, is just a sinusoid, but it is more stretched, while the top one is just a radial pulsation. They are combined together to create a little bit of a more complex pulsation pattern. I have tested this approach on a Cepheid. I have used SPICE, which is an approach published by Antoine Merin. And SPICE takes observational data and fits radial and temperature and a few other parameters profiles to these observations. I have taken these profiles of temperature and radius. I have modeled the spectra with SPICE, and then I have recovered mock photometry. And the result is the modeled curve and the observations that were used to obtain these profiles from SPICS. So I have done a full circle and we find these results acceptable. So there is this little bump here, but Cepheids are generally not as simple. So one could think in general that, oh, it's just one pulsation mode, but they are also pretty cool. So various effects have to be accounted for more than just the radial pulsations, which, in all honesty, haven't been accounted for. Just the fact that it's on the bound of the parameter grid for transformer plane can be a little bit of a problem, but this was just a basic sanity check for the pulsations. And I think it's all right. Photometry is very cool, but of course that is not the end goal of this software because otherwise we wouldn't have to take that many effects into account. So the final goal for pulsations is to study the line profiles. So here the amplitudes are pretty dramatic. If we were to tackle solar type stars, of course the amplitudes would be tiny compared to this, but I have included this so that it's easy to see the changes in the line profiles. You can see that if we include higher order modes, especially this one, the line profiles change much differently. So it's not just wiggling with the Doppler shift. Now it's really a line change. And I would be very interested to see what can we recover from that. The biggest problem here will be the precision. So this is more of a solar type star and a solar type oscillator, and you can see that the flux residual, so that is the difference between the flux and the mean of the line, it is just tiny. So now the question will be, will the fact that we will have access to a lot of lines be enough, or we just have to wait for a huge, huge telescope? It will be, I think, mostly a feasibility study. Things might get easier with other types of stars. Maybe solar type stars won't be feasible, but other stars will. And I'm excited to tackle that in my future work. I will now move on to spots.
Yeah,
So
sorry,
spots
just
are,
a heads up that we have 3 minutes maximum.
yes,
And then, yeah, let me just wrap this up.
it's all
Thank
good.
you.
I'm
Yep.
wrapping up. Thank you so much. So spots can be defined within any parameter that we are interested in modeling. We can model temperature spots, then we can see basically all spectrum will change a little bit because temperature has a huge effect. But we can also study individual lines. Here, this is also a temperature spot, but this time I have included a bit of a brightening ring around it, which is a little bit more realistic. The spot is still huge, of course, but we can see this specific calcium line wiggling a little bit. And this code was also produced with just a small snippet of code that just empirically simulates a line. So that is also absolutely possible. And then we have transits. So for binary stars, we can create double spectroscopic binaries. We can see that indeed the lines will be shifting as expected. And if we already have occlusions implemented, we can add planetary transits. I have slowed it down so we can see the planet transiting. And oh, sorry, this is not temperature. This is the occlusion on the star. And here I have combined a big spot and a planetary transit. So there are two animations at the same time because one is the planet that is just orbiting, slowed down just for this little moment where the planet is actually eclipsing. So you can generally see this trend of a dip in luminosity due to this huge spot and a little planetary transit. So this is how I want this software to be. I want it to be useful for cases like this, where we can just stack various effects together. And my dream is to make it much easier to validate, oh, but maybe this little variable is due to pulsations, and we can quickly check that. The code is published on GitHub. The paper is in review, so we will be implementing a few other things to answer the reviewers' requests. But it is on GitHub, so even though it's work in progress, you can check it out. And I think this is a very good opportunity to collaborate because I was busy developing the code, but I can generally choose just one application to do on my PhD. And I feel like I would love to collaborate on various things. For example, if you have a synthetic spectra grid, this is basically just a matter of let's try to create a model based on that, because the training can be run on anything and then tuned because we can see how it performs. And if you have application examples or some observational data and you think this would be useful, please do reach out. Yeah, I really like talking about various ideas. And once again, thank you so much for inviting me. It's very exciting. And
It was a
thank you
great
so much
talk.
for your
Thank you.
attention.
Yes, and also very exciting. Yes,
Thank
especially
you
for
so
us.
much.
So yeah, I mean, I'm opening the floor for questions and comments. If anyone wants to chime in or
Yes,
even brainstorm
maybe.
ideas, please go ahead.
Thanks so much, Maya, for your presentation. I was really looking forward to this. I had seen your paper appear in the archive, and I thought, I really need to reach out to her.
Oh, thank
It
you. This is
hasn't
amazing.
happened
Thank you.
yet because I'm in the middle of a move, but yeah. But anyway, I really think this is very exciting stuff.
Thank you.
Um, so since you mentioned Cepheids, and that's kind of my thing, are you aware of the Veloce project, the Velocities of Cepheids project? We've been collecting spectra for 200 plus Cepheids, time
Hmm.
series spectra for more than a decade, and we had a data release in 2024. Where we
Oh,
published the
that's
radial velocity
amazing.
data. We have not yet published a spectroscopic time series,
Hmm.
but we have a series of paper called the Veloce Modulation Zoo, where we look into additional signals that you can see in these spectra. And some of the stars have rather high signal to noise, others are rather low signal to noise. So this is more that invitation that I'd really like to talk to you in particular to sort
Yes.
of identify what maybe the origin is of the signals that we see, because that is something we can figure out the periodicities, but we don't necessarily know what we're dealing with. And so being able to
Hmm.
distinguish maybe between spots or non-radial pulsations would be really fantastic.
Yes.
Um,
That sounds amazing. We definitely have to chat more about it. Um, so sorry, just it's a stupid question, but Veloce, does it come because it's not with the Veloce spectrograph by any chance?
no, it no, no,
It's
no.
like
It came
a
out a little bit before. I'm just posting the link to the paper, to the main paper
perfect.
on the chat, so you can see it. It's
Perfect.
just the acronym for velocities of Cepheids and
Right,
was
right.
conceived independently of that spectrograph.
Right, yeah. It's a funny coincidence because I am sometimes observing with Veloce here on ANU. No, but it's fantastic. This is a perfect use case. So I would love to talk more about it. Usually, the only limit of jumping into a use case is just the spectral grid. But now I have finished creating. Well, creating is a bit of an overuse because nowadays coding with codecs is getting a bit easier, and it was actually very easy to create a wrapper for turbo spectrum to run it on our local supercomputer. So I think it will be much easier now to create dedicated grids for specific use cases. So let's definitely chat
Cool.
more because I think
Mhm.
it might be very feasible and very exciting too. I'm very interested
Excellent.
in pulsations.
Great. I also have a question for you.
Mm.
So here you were speaking more about the parameter estimation, etc. Something that we are very interested in WST is alerts detection or anomaly
Mm.
detection of objects. So I was wondering, would you have some ideas of how this code could be used for
Mm.
that kind of work in WST?
I think that's one conceptually simple use case would be if we run in a validation work, maybe we could just create a lot of training examples of various things we would expect for just a classifier or something that is a machine learning anomaly detector.
Hmm.
Because once we have a good physical pipeline, then producing a lot of spectroscopic time series, I hope it would be very easy. But that's my goal to make it easy. So,
So
um,
this is if you have a model underlying that gives you a physical idea of what the object is, right? Is
right,
this something
yes.
that you could do in a relative sense, just purely empirically by comparing maybe with archival data or with prior
Mm.
observations?
Right, yes. So that is something I feel like that is my current step. So I would like to run much more benchmarks because
Hmm.
our emulator has been trained on synthetic data only, and
Hmm.
I think it's only fair to start doing the joint, so both simulations and observations. So it would be great to have more understanding and comparison to, okay, do we recover the observations well? Are things like we imagine them they would look like? But I think for anomaly detection, the main strength here would be, okay, we can definitely create a huge mock catalog of expected time series of spectra for things that are, in our understanding, uh, maybe not normal, but common.
Hmm.
And then we would have a good ground to train anomaly detector that's based on machine learning. I was also thinking of where
Hmm.
would it be useful to create a big mock catalog, uh, whether there are areas where we don't have access to a lot of simulations right away. Because once I am done with empirical evaluation, which is very much needed, I hope it will be easy to do. That's what I'm trying to create, at least.
Hmm. Sounds excellent. Thank you so much.
Thank you so much. These are great questions and very excited about the Cepheid stuff.
Other questions? Comments? Anyone from the audience?
Well, if people are shy, I have another question.
Yes, of
Uh,
course. I mean,
But
Teresa is
Teresa
there.
has a question.
Sorry, Richard. Sorry, people are muted. Please go ahead, Teresa.
I also would like, it's more a comment than a question, would like to be in contact with you because I'm studying spectra of type 2 Cepheids, and in particular, I seen in one of your slides that when you apply, I don't remember what to the models, you can see in the gradients something like a p sigma in the lines, I think.
It's in the lines.
Yeah, no, it's the next slide. Yeah, yeah.
Mhm.
because differently from classical Cepheids, with type 2 Cepheids, we have more p sigma in H alpha and H beta, and it will be very interesting to see. I mean, to give a more physical explanation to.
Mm.
So I think a comparison would be very nice.
Yeah, yeah, absolutely.
Yeah.
Yeah, I don't know that much about Cepheids yet, but it sounds great.
Yeah.
Yes, yes, please. I will reach out to try to remember.
Thank
Yeah,
you.
this
Thank
is
you
the
for
right community of
Thank
Cepheids.
you.
We have way too many people
No,
working at
that's
Cepheids
great
in this
because
working group.
that is
This
great
was really
because
the plan.
Never
honestly,
enough.
Never enough.
yeah,
Yeah, what
I
can I
was
say? Yeah.
actually a bit sad because I chose Cepheids as my example because I found SPIPS, which seemed like a very good code to compare against, but no one in my institute does Cepheids, so people just said,
Okay,
"Well,
so
it
yeah,
looks
you're with the
right,"
right
but
crowd.
that's
You
good.
have stepped in the right crowd, yeah.
That's great. That's
Okay,
great. Yeah.
Evelyn, do you have a question? Do you want to go ahead?
Yeah, now you can
Okay,
hear me.
thank you.
Hello, Maya. Thank you very much for this very nice presentation and
Thank you.
wonderful work.
Thank you.
So I'm just to let you know, I'm working on young stars, so no Cepheid, sorry, but young stars are also great to study,
That's all
and
right. Yeah.
they are very variables, and for many reasons. And one of the things that that is not in your code, but maybe could be very interesting to add is that we see a veiling adding to the spectra of the young star.
Yes.
Yeah,
Yeah,
you
yeah.
know
So,
what I mean
sorry,
by
do you mean
veiling?
the dust or
So
the?
it's not dust, it's an additional
Mhm.
continuum that is usually created by the hotspot at the surface of the star.
Oh, okay, okay.
So these young stars have hotspots because
Mm-hmm.
of the accretion column at the surface of the
Mm-hmm.
stars. That's a different kind of cool spots. So the hotspots could be very
Yes.
interesting to add, and also the veiling. But the veiling is just a continuum that
Mm-hmm.
is wavelength dependent from the UV up to the near infrared, and
Right.
um, and that's something that would be very interesting, and that comes to my questions because uh, one of the difficulties we may have, and it takes lots of time, is try to get the temperature of the stars, including the effects of the veilings and hotspots.
Mm.
And I was
Right.
wondering if this is something that, before studying the variability, this is something that could be done easily with your models.
Yes, yes. So, yes, but also, I actually didn't include that in the slides, but so there was a study which showed that if we don't take even just quite to some extent understood cold temperature spots into account and we try to recover temperatures, they're offset, right? So that was also my motivation that if we uh, like even by considering a coverage percentage of a star, even if we include that, let alone a more complicated model, we should obtain much better estimates. So that is also something I would love to see this code being used for, just better parameters being inferred.
Yeah,
Uh, the biggest trick here, I think, would be the degeneracies. But with spectroscopy, I think that should be much better because with photometry, we have these problems with spots being, well, just degenerate. They can be anywhere. So hotspots are definitely already doable because this is just a special case of a spot. So the spot is very arbitrarily defined. You just put the change in parameter and the parameter. So that is done. I haven't studied the degeneracies and failure modes when recovering from spectra yet. So that is something that it will definitely be a problem in some extent, but I hope that with spectral time series there will be enough information to have more robust inference results, or at least it will be good enough. So sometimes we don't care about recovering the exact location of a spot, but we can tell how many spots there are. But with temperature, I would hope that would be precise enough. Yeah. Yeah, that's a fantastic use case.
Yeah, what we're using are spectra, either optical
Yes.
or near infrared, and soon we will have together from near UV up to the K-band spectra at the same time
Yes,
for
fantastic.
young stars, so that high resolution spectra. So
Fantastic.
it's a lot
Yeah.
of information inside, and it would be great to have
Yes.
to try at least a tool
Yeah.
to get parameters. Yeah.
Yes. Yes. Sounds great. No, thank you. That's a great use case. I never studied youngsters, so I know that they have a lot of interesting effects. Uh, so far, the only effects I genuinely am not sure how to include are anything related to dust, so like very fast spinning stars. I'm not sure how to include. I mean, there's surely a way. It's just not trivial to include, for example, a disk of dust. So that would be problematic. But anything that happens on the surface, I hope that would be manageable with the current framework.
For most of the stars we study, we are dominated by the photosphere, and the dust
Yes,
is
yes.
only starting to be seen at later wavelengths or at cooler.
Right. Right.
Mm.
No, thank you. That's
I
fantastic.
agree with you. That's a different problem,
Mhm.
and
Yes,
but
yes, that is a bit of
for
a
optical and near infrared spectra, it's okay.
right. Great. No,
Thank you.
sounds fantastic. I will reach out to.
Okay, I think we can now cycle back to Richard if you want to ask
Yes.
another question, one more question.
Yes, thanks. So let me just gather my thoughts. I think you said that you wanted to improve the age estimation with spectral time series, and I was just wondering
Mm.
how you see that working out in the sense that how can the spectra give us further information on these age estimates?
Yes. I will just change the slide because the line is wobbling so much. It's distracting me a bit. So, but this is actually the slides which was connected to the astroseismology part. So basically, I would like to see, I mean, in principle, this information is there, but the line profiles will change with even modes of pulsation. The question is how feasible in the future is to recover that information. Um, I have been talking to a few astroseismology people, so it's not even my idea, but they basically all repeated that maybe if we had the even modes, we would just simply have much more modes to model the star with, and then the models would be much better constrained. I have myself not worked with astroseismologic modeling, but that's my impression that it's it's just not enough modes for some stars to create very good models, and therefore the age estimates are just reliant on how well these astroseismologic models are. So I would just hope that by adding this information about even modes of pulsations, that would be already an improvement to the astroseismologic model and in turn the age estimate. There are different
So it's
components, of course.
So it's more about detecting the modes rather than any particular information that the spectrum gives you that you need to break any degeneracies in the analysis.
Yes, it's just more
Mhm.
modes. I'm sure
Okay.
there are also other factors, but this is what I had in mind. And I have seen some presentation doing that. The question is just that I'm mostly interested, at least up to now, I was mostly interested in FGK stars, and then the pulsations are very small. So the detectability might be a problem, but that's up to a broader study, I think, to see okay, which cases are doable, which are doable in the future. But yes, long story
Yeah.
short, it's just more modes as for now.
Thanks very much.
Thank you. Thank you so much for the great questions.
Okay, Any other questions? Final comments? Heartfelt interest? No, okay. So thank you
Thank you
again,
so much.
Maya. This was great. It was great having you. And yeah, we're very much looking forward to collaborate with you in the future, I guess.
It would
And
be
we have like so
amazing.
many interests. Yeah, like I hope like you connected with the right people. It looks like it.
No, for sure. It does look like this. Thank you
Yeah,
so,
like
so
this is
much
also
for
a
inviting me.
networking hub. Yes. I
Oh, yes,
confirm.
absolutely.
Okay. So see you around. Take care, everyone. Thank you. Bye.
Thank you
Have a
so
nice day.
much.
Thank
Thank
you.
you. Have
Bye-bye.
a
Bye.
Have a
nice
nice
day.
evening.